Let's do a quick review of constant acceleration kinematics, and then we'll take a look at rotational kinematics and find out we already know a lot about this. This video is mainly for people who want to review what we did in class for rotational kinematics, or people who were absent. So if you were there and figured everything out, you probably don't want to go through this because you saw it in class. So when we did kinematics before, we had this hierarchy of graphs: position, velocity, acceleration, with position on top. And the idea is we can derive the equations we need and the relationships we need if we know how to go from one graph to another. And if I want to go down from position to velocity, it's either slope or area. If I take the slope, I'm dividing the y by the x, and the units would be meters per second. And those are the units of velocity, so I know taking the slope gives me the velocity. Same thing going from velocity to acceleration, dividing meters per second by seconds gives me the units of acceleration, so I know it's slope. And then I know going back up it's got to be area, right? And you can check it by multiplication. Area is always multiplying things. Acceleration times time gives me the units of velocity. And the area under the velocity graph is going to give me my change in position. And if we were to sketch what constant acceleration graphs look like, this is just horizontal, right? A equals A. This is, if the acceleration is positive anyway, a straight line sloping up with a y-intercept of v0. So the equation of that line is v is v0 plus at. And this is a parabola, and it starts at x0, and the equation of this line is this. And so you should know these. There are also some other useful equations in kinematics. Average velocity is the initial plus the final over 2, and average velocity is the change in position over the change in time. Key thing is this always works. This only works for constant acceleration. Otherwise, it's approximate. Then we had another one. Let's see if we can derive it. Let's take this equation and solve it for the change in position, average velocity times the time. Let's take this equation and solve it for time. And so I'm going to eliminate time from this equation, and I'm going to put this in for the average velocity. And so now I have this, and if I carry out this multiplication and rearrange it, we have this other handy equation that came in to play when we weren't given the time in a problem and we didn't need to know the time. And so you should see if you could work out this derivation on your own. It's good practice for algebra. And so why are we going through all this? Well, now we're going to have an object going in a circle, and I want to track its angular position theta, its angular speed or velocity omega, and its angular acceleration alpha. So these are all different than linear kinematics, but it turns out the relationships are the same. And so theta would be in place of x, omega in place of velocity, alpha in place of acceleration. And if I want to go down, I take the slope. Radians, R stands for radians here, over seconds. Y over x is radians per second. And if I take the slope, radians per second over seconds, I get the units of angular acceleration. If I'm spinning and I'm speeding up the rate of spin, the angular velocity, I have a positive alpha. If I'm spinning and slowing down, I'd have a negative alpha. And then going up, it'd be area. And you can check that with the units. Radians per second squared times seconds gives me the units here. And same with this. And if we had constant alpha, it would just look like that. Alpha equals alpha. And this would be a straight line with an omega 0 here. And this is a parabola with a theta 0. So the equation of this line looks like that. Equation of that line looks like this. And there also are equations for average angular velocity. And so it sure looks like we're just overloaded with equations now. But look at a pattern. All the constant angular acceleration equations can be obtained from the linear, constant linear acceleration equations. Everywhere you see an x, put in a theta. If you see a v, put in an omega. See an a, put in an alpha, and there you go. And so compare these with the equations on the previous screen. Or let's take the one we derived and convert that. So instead of v and omega, instead of V0, omega 0, instead of A, alpha, and then theta and theta 0. And so that's a new equation, but in a way you already know it if you know these things. So let's use these equations to do some problems. And so we are going to turn a turntable off when it's spinning at 45 RPMs, and we're going to time how long it takes to stop and calculate the angular acceleration of the turntable while it's stopping. But here's a problem. 45 RPMs, I need to be in radians for all those equations to work. And so first let's convert the angular velocity from RPM to radians per second. So you should know how to do this. And so if you don't, then keep watching. If you do, pause and do this yourself. This was on the last test, and most people knew how to do it. And so 45 rotations per minute, write it like this instead of RPM, and then it's easier to come up with the conversion. I need to get rid of the rotations and be left with radians. And so I put the rotations in the denominator, radians in the numerator. 2 pi radians equals 1 rotation. Now I have radians per minute. And I need to get rid of the minutes, so that goes in the numerator. And I want seconds in the denominator. And so the minutes go, and I'm left with radians per second, 4.7 in this case. And so let's figure out what the time is. And so this is a little video. And so record player's playing. You're going to see my finger come in and turn it off. Start your stopwatch now. And it's slowing down. And stop. That was about 9 seconds. You could time it yourself if you want. You might have been surprised you could hear the record still. That's because the cartridge and needle act as a little generator and produce an electric current that produces the music. So as long as the amp is on, we can still hear it. And so for kinematics problems, we assigned variables, and that's step 1. Look at what the problem tells you. And so I know that the initial angular velocity is 4.7. We already worked that out. And it's stopping, so the final is 0. It's worth writing that down. And then we timed it, and it was about 9.4 seconds. And the initial position is 0. And that's usually the case, and we want to solve for alpha. And so what you do is you take a look at all your equations. And so if you didn't write the ones down from the previous screen, you may want to go back and do that. Or maybe you can just write them all down from memory. And then look at them and see if there's one that's going to work for this problem. One that contains what we're given and the unknown. Those are the easiest problems. And so there is one. This one, I know omega 0, and the time, and I want alpha, so this is an easy problem. You just put the numbers in and solve. But first, solve the equation for the unknown algebraically. And so that is advice I've been giving all year. And if you've been nailing these kinematics problems and everything's great, then keep doing what you're doing. But if you've been making mistakes and having problems, do it this way. Assign the variables. Write down the relevant equation. Solve it for the unknown before you start messing with numbers. You will do better. Give it a try. Now we put in our quantities. And omega is 0. Omega 0 is 4.7. Divided by the time, I get negative 0.5 radians per second. And so people who didn't do this step might come up with positive 0.5. And you would miss one you should know how to do. So do it my way until you're getting everything right. So let's do a different one now that we know alpha. What if we turn the turntable off when it's going a different speed? How long will it take to stop? So we'll have it going 33 1/3, and we will turn it off, and we're going to try and predict the time to stop. And so first, we know we need to convert to radians per second. So try that on your own. Pause the video, and then we'll go through it. Okay, we're back. And so hopefully you did that. We went through in detail before, so take some time to look at that if you had trouble. But it comes out to about 3.5 radians per second. Now we assign our variables. I know the initial is 3.5, final 0, and we're assuming alpha is the same. What is the time? So you look over your equations, and you should also, once you pick it, don't just start messing with it. Write it down as it is. Then you will learn it. And so if you've been saying, oh, I just don't know all these equations, it's because you're not using opportunities to practice it. Staring at a sheet of paper with a bunch of equations written down doesn't help you that much learn them. But writing them down every time you need them, that's going to help you learn it. Then solve it for the unknown. In this case, it's time. And so it's change in angular velocity over the angular acceleration, and substitute in the numbers. So now I'm ready for the numbers, and it comes out to about 7 seconds. And so let's test that out. And so I have to go back to this. You're going to see my finger come in and turn it off. And I'm started the stopwatch. Here we go. And I got 7.3 seconds, so pretty close for just doing it by hand. And so it sure looks like the acceleration is pretty constant. Let's do a different one. Let's get the change in angle when we turn it off when it's going 45 RPMs. And so now we're predicting theta. And so assign the variables. And the initial is 4.7. We already converted 45 to 4.7. It says stop, so I know that means omega final is 0. It's worth writing that down. The initial position we'll just say is 0 wherever it's at. And alpha is still negative 0.5. What is theta? So look at your equations. There are different ways of doing this one. In this case, I picked this equation because I'm not given the time and I'm not asked for the time. And this has everything in it except our unknown theta. Solve it for the unknown. You could just say this equals 0 if you want. But if you don't, that's what you get. Put in your numbers. And you get 22.1 radians. Another approach you might try is use alpha and these to solve for the time, and then use the time to figure out the change in angle. Give that one a try. And so 22.1 radians, let's check that, but what is 22.1 radians? Let's change it to rotations. So that looks trivial, right? But many students make mistakes here because what they'll do is they'll divide by 2 and then multiply by pi. And so you have to divide by 2 pi, so use parentheses or approximate 2 pi is 6.28. So let's see. This is the position that the turntable is going to be in when I turn it off. This little circle is going to be right here. And so let's do that. So you'll see my finger come in here and turn it off when the circle's right here. There. So we're on once, twice, 3 times. Not quite 3.5, but close enough for government work. And so again, the angular acceleration looks pretty constant here. There might be some variation accounting for that. So let's take a look at another relationship we need to know. We need to be able to go from angular quantities to linear and from linear back to angular. And some of this is review. Here's an angle defined in radians. The arc length is x, radius r, theta in radians. It would be the ratio of the arc length to the radius. This you need to know. That is a fundamental idea. And I find a lot of times students don't know this. What they do know is there's 2 pi in a circle, but they have no idea why. Well, it's because the arc length for a complete circle would be the circumference divided by the radius, and I get 2 pi. Really 2 pi nothing, right? But we put radians as a placeholder. So radians are a dimensionless measurement. And so I could take this equation and solve it for x, and so I get x is theta r. So however you want to learn it, that's fine. Let's do the other ones. How about omega? The average angular velocity is change in angle over change in time, 2 pi over the period. And the average linear velocity is change in distance over change in time, which would be 2 pi r over the period for a complete circle. And so notice this 2 pi over the period is omega. And so the average angular velocity, average linear velocity is the average angular velocity times the radius, and that's true for instantaneous too. And so this works for whatever the velocity is at a particular time. And so do you see a pattern here? What do you think A is equal to? And so if I want a third one, A is equal to, how would that relate to alpha? Well, let's see. And so A is change in velocity over change in time. And I can take V as omega r and put that into each V. And so I get this. I can factor out the r, and I get the linear acceleration is omega minus omega 0 over the time. Well, that is what alpha is. This is the angular velocity versus time equation solved for alpha. And so A is alpha r. But notice the pattern. If you have the angular quantity in radians, you multiply by the radius to get the linear quantity. And so that's true for all three. You need to know these in this unit. And so these we've run into before. This one is new, but if you know these two, you can figure that one out. And so just some quick calculations here. When the needle is going over the record, what is its relative linear speed? It's at a radius of 0.14 there, and let's say it's going 33 1/3 or 3.5 radians per second. You should be able to find V. And boy, if this is right in front of you, that's easy. If you're having to come up with it, a little tougher, but it shouldn't be a tough problem. And so this would be 3.5 radians per second. This is 0.15 meters. Notice the answer just comes out in meters per second. Radians is just there as a placeholder. You could have just said 3.5, 1 over seconds too. How about when the needle is closer in? And so now it is here at a radius of 0.07 meters. What is the linear speed at that time? Well, it's going to be slower, right? V is omega r. If I have a smaller r, I'm going slower. What about if I turn it off here? What is the linear acceleration relative to of the needle relative to the record? And so when I turn it off, alpha is negative 0.5, the radius is 0.07, and so A is alpha r, and so it's negative 0.5, and that's radians per second squared, and that's meters, and then notice no radians over here. It's just a placeholder. And so you need to know these relationships. Write those down, tattoo them on your arm, whatever it takes, know them. Let's do one more example. This one's a little different. The turntable is going to be going at 45 RPMs, and I'm going to change the speed by pressing this button here, and the motor will slow it down. And so alpha is not equal to negative 0.5 radians per second squared now. It's something else. It's actually more. So we don't know alpha. We will know the time, though. We can measure that. And so let's assign the variables. And so the initial is 4.7. The final, 3.5. That's 33 1/3 in radians per second. And the time, 1.2. And you can get that by timing this. And so let's do that real quick. Just show you how I did it. And so you're going to see my finger press this button, and this red light here will come on, and then there's a delay before the green light comes on. The green light comes on when it's going 33 1/3. So the question is, how much time from when this red light comes on to when this green light comes on? So if you want to try, pause this, get your stopwatch going on your phone or watch or whatever. So here we go. So you can see my finger come in, and that goes on, start, stop. And so I did that decent number of times and came up with the 1.2 seconds. And so we've got our variables assigned. Now you select relevant equations, look and see what might work. There's several ways of doing this one. You may want to try and find a different way. It occurred to me to try the average angular velocity equations, because I know omega 0 and I know omega, and so I can come up with the average angular velocity, and then I know the time. I can get theta with the other average angular velocity equation. Using these two together can be very useful. And so this one's already solved for average angular velocity, and so 4.7 plus 3.5 over 2, 4.1, and then solve this equation for the unknown, and I just set theta 0 to 0. And so it's just 4.1 radians per second times 1.2 seconds, 4.9 radians. And so that should be the change in angle. If you want to try another way, notice we don't know what alpha is. It's not negative 0.5. Solve for alpha. You know the time, you know omega 0, you know omega. Get alpha, and then see if you can solve for the change in angle that way with a different method. And so this is 0.8 rotations. Remember, dividing by 2 pi. Be careful doing that. And so it should spin about once. And so this is where it is when I hit the change in speed button. And so let's see where it is at the end. So you're going to see my finger come in, go, and so it's about here when the green light comes on. So I took a still of that. And so this, you can see the green light has just come on here, and I did a frame grab, and so it's about here. And so this would be about 0.75, so it's almost right on 0.8. So that worked pretty well. So again, this is review. You should be able to do the WebAssign now, and I will be putting problems like this on the quiz. And so good luck with that.